Science time. Science time. Is that funny?
Yeah.
Well, let's write down science time, and we're going to write down the topic. Can you guess what the topic is titled today? Yeah, let's just call it as the book calls it. Behavior of. We could call this waves, just in general, but we're going to specify light waves. All waves behave in the three main ways that we're going to talk about today, but we're going to talk specifically about light waves because we've already kind of talked about the ways that waves can behave in general. Now we're going to talk about specifically for light waves. The first thing we're going to do, as I told you, is we're going to draw the diagram you drew for your bell. We're going to label together. So first of all, if I'm drawing a light wave, what should I do first? What kind of wave should I draw? What's its wave form? Transverse. I'm going to draw a transverse wave. In this drawing, we can't tell from the way it's drawn so far, which way is the energy transferring? Just pick one. Yeah, say the word so that people who are watching
To the right.
Right. We're going to say that the energy is transferring to the right. Energy transfer to the right. Because it's a light wave, what else is going on here at the same 90 degrees, but in the opposite axis? Right. There's another transverse wave, which we sometimes call a magnetic wave. So we're going to pretend that this is supposed to be 3D. So like if you're looking down at it, kind of at an angle, this one would be, I don't know how easy this is to tell in the video, but this one would be, like the energy is going this way. So the one wave is going up and down like that, and then the other wave is going left and right like that. So we can say that the black is representing the electric force, and the green is representing the magnetic force. We think of those things as being perpendicular to each other because of something in physics called the right-hand rule, which we will talk about when you're in physical science next year, but for now this is sufficient. Well, that is, the drawing is sufficient, but we need to do what else with it? Peyton, what's so interesting about what Angie's doing on her computer?
I was just going to tell her that picture's drawn because
Okay.
a light wave.
Because we're all going to do it together, and we're all going to do it right now. So what should I label it as? Okay, fine, I can start with that. I guess that's not really a part of it. I mean, that's fine. What should I label the parts as, though? Crest. Where's the crest?
The crest is the very top, and then the trough is down in between the two crests. And then the line in the middle is your wavelength.
Let's be
that would be the wavelength.
Let's call this baseline.
Baseline, yeah. And then underneath there would...
So from one crest to the next, we call it, as Peyton already said, wavelength. We have a special symbol for wavelength. Do you remember what it is?
It was like a cube.
Lambda.
It's a Y, and then it's like...
It's like
Whatever. Lambda. And then we have another kind of distance that we talk about frequently. Ooh, the amplitude, but I also almost said frequency, but this is the amplitude. So the distance from baseline to crest or baseline to trough is amplitude, and then how many waves pass in a certain amount of time is called the frequency, right? This is the anatomy of the wave. We've talked about this before. In fact, we have it on video talking about it before, so this is review. What I want to draw your attention to is that this is a light wave, and we can tell because it's transverse wave. There's no movement of matter, right? It's not a material wave. It's not made of matter. Can it travel through a medium? We've talked about this repeatedly. It can, but as Colin says, it doesn't have to, right? So this can travel through a vacuum. Hayden, question?
So the amplitude, it's like, so that the baseline is from there to like the top of the top of the crest or something like that, right? Okay. So how is that measured? Like, how can you measure that? Like.
So for a material wave, it's pretty easy. We can just there's better ways, but we could stick a meter into it. Think about like a water wave, and we could measure how high up the water goes. That would be the amplitude. For this, you know what? This is actually a really good question, Peyton. Do you know what we said already? The greater the amplitude, for a given frequency of light, the greater the amplitude, what else is greater? Energy. And so what we do, Peyton, for light is we measure the energy of the light wave, and from that we can extrapolate the amplitude. Because for instance, if we know the energy output, we know the frequency, which is the other thing energy depends on, then we can find what the amplitude is. And there are instruments that do that, right? We can't just look at a light wave and tell it, but there are instruments that do that. But when I say we can't look at a light wave and tell it, we kind of can. We can't tell the amplitude is 0.44 nanometers, right? We can't say that, but we can tell really easily with light whether the amplitude is the same or different. How? What does the amplitude change about the light?
the brightness.
The brightness, right? So I can tell, I can tell this a lot when I'm driving on the highway. I can tell if the amplitude of the oncoming car is because they have their high beams on or their low beams on, right? It's pretty easy to tell, right? Because the amplitude is greater in the high beam.
Yeah.
Is the frequency different?
No.
Nope, because it's both white light, right? It's both a combination of all the frequencies
It's
of the
just
light. There probably is a little variation, but since we can assume they have roughly the same frequency, but one is brighter, the amplitude must be greater on the brighter one. All of this is review. Now let's talk about another thing that we've talked about already, which is how can waves, when they interact with a new medium, how can waves in general behave? There are 3 ways. We already had a video about this, but 3 ways waves behave entering a new medium. That is, if they're going from, for instance, a light wave going from the vacuum of outer space into the atmosphere, or maybe from the atmosphere through the glass of the window, or a sound wave moving from the air, which my voice is passing through your little hair covering your ear, Leo, into the air in your ear. Anytime a wave of any kind changes medium, one of 3 things is going to happen. Tell me what they are, real quick. Reflection.
Refraction.
Transmission is one for all waves. We'll talk about refraction in a second. But the other thing that can happen in general is that it can be absorption. And we have talked about these before. If you need a review, you can watch the video, you can look back in your book, you can look back in your notes. But we know what these things mean, right? Now we're going to talk about what you also said, refraction. So refraction is kind of a special case. When refraction occurs, it's really a type of one of these. Which one?
Reflection.
No. Did you read your book? Someone who read their book and actually knows the answer say it, because there's only 3. We don't want to guess all of them before we get it right. Refraction is a special type of transmission. Because what's happening is, so for instance, the way we think about it as a law is if we have a glass of water, which I'm going to represent with blue, because water, as we know, scatters blue light and absorbs the other color's light. You wouldn't notice in an actual cup of water, but anyway, some light, or we have a glass of water, we're going to have some light coming in, a wave of light coming in, which I'm just going to draw the electric part of the way because it's easier. Refraction occurs when it is going to be transmitted, it is going to go through it, but first it's going to do what? What must happen as it goes into this water? A little bit and a little bit, but primarily what? What's going to happen to the speed of the light as it moves from air? There we go. Because it slows down, it bends. Okay, so let's write that down. When, and we call this an incident light wave. What in the world does incident mean?
Something that went wrong.
No, that's, well, no, your accident.
By chance?
No, maybe. I guess we don't really use this word in this way very much in our normal speech. When we say an incident in our normal speech, we probably mean something that happened, maybe something that went wrong. But for something to inside means it kind of comes in, right? So the incident light wave, the light wave coming in. You can kind of think of it that way with like an incident in your life. It's something that came up, right? Something that arose. I had an incident where I fell down the stairs, right? I had an incident where I slipped on the ice and broke my kneecap. Right, but that could be something that came up, and it's kind of the same way with this. But when we say an incident light wave, that means the light wave coming in. When an incident light wave enters or changes velocity, why? Because it's doing what? Because what else is changing? What's the
frequency?
A little bit, but the medium changes, right? So therefore the velocity changes. When an incident light wave changes velocity, it bends. The classic example of this is we put a pencil in a cup of water, and even though we know the pencil's straight, this is going to be a pencil, it looks to us like the pencil is bent. Because the light has a different speed in air, which is what this light is traveling through to get to our eyes, from water, which is what this light is traveling through to get to our eyes. So it bends. And that bending makes it seem like the pencil itself is bent. There's a picture of this in your book on page... it's a straw in your book, I guess. On page 68, and it's not nearly as severe as I drew this. This comes up a lot, I don't know how frequently this entire thing happens, but if someone has been bow fishing, have you ever been bow fishing?
Yeah.
It's something that a lot of cultures have done in the past, and some people still do for fun. But when you're bow fishing, a good bow fisher knows about this, and so they always aim, depending on where the light is, a little bit above or below where they see the fish, because where you're seeing the fish is not where the fish is, because it's under the water. Same thing with the straw. Where you see this straw, the straw's not actually there. The straw is actually here, but it looks to you because of refraction like the straw is here. Does that kind of make sense?
Yeah.
So it's the same thing with bow fishing. Or, I guess it doesn't have to be a bow, but if you're like hand fishing, right, this is how some of you fish, caveman.
Or you use your thumb and you wiggle it. And then
Yeah, that probably, you don't have to look at that, so that one probably doesn't count. I know what you're talking about, but you don't have to see that one.
Wiggling.
Cyrus.
So like, how, like, if you're at a pond and like, you know, like the sun's shining over just a little bit, like, your fish seems like so, like, big under the water.
There, that's the other thing. Is that another thing that can happen because of this refraction is magnification. In fact, if you've seen a magnifying glass, which its job is magnification, if you look at it from the side, it just looks like a normal piece of glass except it's bent like this. And the reason that this is called a convex lens, the reason that this works is that as light comes in, it's bent, and so when it comes out, it's spread out more. It's just that simple, right? The light comes in, it bends, it widens, and so when it comes out of the lens, it's wider, and so to you it seems bigger. Same thing happens with water, right? If you look down, you're like, oh man, I got to get that great big femur. Catfish. Let's use femur. I gotta get that great big femur that's on the bottom, and you go and you reach it and you pull it, you're like, this is just a little dinky's femur. I don't want this crap. Don't say crap. But that's because of the refraction of the light, because the light has bent due to the change in medium. Let's see. Prisms. A prism is a special case of refraction where the light, a prism is designed, and we talked about this a little bit in a previous video, a prism is designed that it takes incident white light. What does that mean the white light is doing? Coming in white light, and it bends the different frequencies of light differently. I should use different colors for this. What are the colors of light we might get from this?
Red, orange, yellow.
Well, hold on. Red.
Red.
Oh. Orange. Yellow. I hope I'm not like violating copyright by saying this to you in a video. Yellow, green, blue. This takes a lot longer than just saying it. Blue. Purple.
That would get Mr. Prime demonetized
There we go.
on YouTube. Probably.
Nice. Whatever. Because these different frequencies of light, they have the same speed, we know, but they have different wavelengths. And so a prism is specifically designed so that the refraction that occurs with the red light is either less or greater. This may not be accurate, it might be the other way around. Either less or greater than the purple light. So they bend differently so it comes out as a rainbow. All the colors of the rainbow. We talked about how we see colors, right? Where if something is absorbing all the colors except for blue, what does it seem to us like that color is when we look at it? Blue, right? It's reflecting blue light. So what colors of light is Angie's shirt absorbing?
All the other colors.
All of them but blue.
Well, that's actually a
And
jet.
there's some brown on there too.
That's a jet.
Okay, and then the last thing, I think this is the coolest stuff. Mixing colors. I'm going to erase some of this, and you write this heading in here. Do you have questions before we move on about refraction? We had already talked about these three things in general, but do you have questions before we move on about refraction? Oh, another thing, by the way. We have different words for when materials do one of these, what that looks like. You know the words opaque, translucent, and transparent. Write those down real quick. I'll write them down too. It's some kind of like a little side note. Your book doesn't talk about this, but it's kind of important to me. Opaque, translucent, and transparent. You've heard of these before. What does opaque mean?
Okay, you can't see through it.
Can't see through. In fact, not only can you not see through it, no light is coming through, right? Opaque. Which of these is occurring with opaque? Which of the three ways light can be?
Absorption.
Absorption, but only absorption? Not necessarily.
Reflection.
Absorption and reflection, but not transmission. In these other two, there's some transmission at least. But do you know what translucent means? Have you ever seen something translucent?
Kind of.
That means
yeah,
what?
It's like
what-
foggy.
Yeah, what this means is
And
that
then kind of like
translucent means the light loose can cross over through it. That means we can see light coming through the other side. For instance, like a shower glass a lot of times is fogged up. And it's a good idea because someone coming in the bathroom, you want the nice light from the bathroom ceiling light into your shower so you can see what you're scrubbing. But you don't want someone to come in to see what you're scrubbing, basically. Because you want to see the light come through, but you don't want to see a what?
A person looking at you.
Well, it's not always just not a person, but you don't want to see the actual image, right? You don't want to see the object itself. And so that's when we use something that's translucent. A sheet of paper is translucent. Can you see my face a little bit through this?
No.
I can.
Well, I mean,
You can see. Well, if I held it
I
up
see
with
the
the light,
other side of the
you can see the other side of the paper, right? Because the light is passing through. You can't read the words probably because it's only translucent, not transparent. Whereas transparent means that we can see an image clearly through something, right? Both of these are largely largely transmission with a little bit of the other two. Transparent, I would say, is mostly transmission with a little bit of the other two. But there is also, if you ever notice, like if you walk by a parked car, you know the window glass is supposed to be transparent, but you can see your own reflection in it, right? So everything, even window glass, even very, very good glass, even if it's supposed to be all transmission, there's always going to be a little bit of the other two as well. Nothing is perfectly transparent. Yes?
Oh, so I have a question. This is probably a stupid question.
It probably isn't. Let's hear it.
So when, like, you put paper, it's like you have a shirt that says something, and you go up to a mirror, it's like upside down. Why is that?
Yeah. Actually, I was just thinking about that last night when I was looking in the mirror. So basically, I'm going to try to draw a pretty rough diagram here. This is Peyton. This is what he looks like. So there's a light up here. The light is shining everywhere, right? It's shining on Peyton's shirt. It's bouncing off the shirt, going in the mirror, and then bouncing into his eyes. And this drawing is not great, but basically, whatever's on the left side of your shirt is bouncing on that side of the mirror, and then bouncing into your eye. And so it seems to you like the dude in the mirror, that's the right side of his shirt. But it's just because they're bouncing in parallel. The light waves stay parallel. And so what was on your left side seems like it's the dude in the mirror's right side because that's parallel. They're lined up.
Well,
Right?
almost like you're looking at yourself.
Exactly. So like if I had a student standing right here in front of me, my left side would line up with their right side. It's the same thing in the mirror, right? Just because the light beams are parallel, so it switches the image around. Does that help? Okay. We talked about those. Last thing, we're going to write this thing about color addition, or is that what I called it before?
Question.
Yes.
Is it the same thing for on your camera on your phone?
Yep. Most phones nowadays have an option where you can turn that off. You know what? It's kind of interesting, not from a physical science standpoint, which is what we're doing now, but from like a psychological standpoint. A lot of people are more comfortable seeing themselves as a reflection. Because that's how you see yourself all the time. This camera, when I look in it, and I can see the image over there, it looks like how I look in the mirror, because the camera has flipped it. The camera doesn't have to do that. The camera could very easily make it so that that's showing up how it is in real life. But I'm more comfortable seeing myself flipped, and so the camera flips it. Kind of as a courtesy to me so I don't feel bad about myself.
Well, we see you different than how you
Yeah, exactly. You see me different from how I actually am in real life because of this reflection.